The purpose of probability is to be able to determine what happened in the past and use that to make predictions in the future. The power in it lies in taking what we already know and applying it to things that could happen in the future. And again, making predictions on the future. So today we're going to talk about two different things that we could do with probability. One is determine how many times something should occur based on how many times in theory it should happen. And then we're going to actually do an experiment and see how many times it happens and if that probability actually correlates to what we would have expected to happen. We're going to find the probability of two different events from the same scenario, which has to do with the number cube, and see how we could use that information to make predictions on how many of something we'd expect if we were going to roll the number cube a whole bunch of times. Now, this is called a theoretical probability. This is called a theoretical probability because this is what we think, like thinking what should happen based on how many total outcomes there are. If you remember, the probability of some event E is always the total number of ways that we could be a success out of the total amount of things that could happen. So in this instance, the probability of rolling a 3, since there are 6 total things that could happen on a regular number cube, and there's only one 3, the probability that we roll a 3 is 1 out of 6, in theory. So in theory, if you were to roll a number cube 6 times, blank, 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 you would get a 3 on one of those 6 rolls. In theory, you'd think you'd probably get a 3, a 2, a 1, a 6, a 4, and a 5 in any order, but in theory, you'd think you'd get one of each of them. Is that going to be the case? No, of course not, and that's what we'll talk about experimental probability later in this tutorial. But for now, let's do the second one. So the probability of getting, in this case, it's the same E, rolling an even. There are 6 total things that can happen. Out of those 6, how many are evens? Well, 2, 4, and 6, so 3 out of 6, which simplifies to a 1/2, 50% chance, equally likely that you will roll an even versus not rolling an even, which in this case would be an odd. So we're going to use the same thought of rolling a number cube, except this time we're going to roll a number cube actually 90 times. And we need to determine, in rolling that number cube 90 times, how many times would you expect to roll the number 3? We know that in theory, the probability of getting a 3 is 1 out of 6. Again, in theory, every 6 times you roll a number cube, you would get the number 3 one time. Well, if we know it's 1 out of every 6, we can use the skill that we learned last unit on proportions to determine that 1 out of every 6 is how many out of 90 rolls. So 1 3 out of 6 is how many out of 90. This is simple cross multiplying and solving. 1 times 90 is 90. Divided by 6 is 15. So you'd expect to get the number 3 15 times. There is another way to do it, a simpler way if you don't like using the proportion skill that we had developed before. You could just say 1/6 times the number of times we're going to roll it. That involves your ability to multiply with fractions, which is 15. It kind of makes sense because if you kind of think about the number 15 and you did the number 15, you could say you could roll the number 1, the number 2, the number 3, 4, 5, and 6. If you split it evenly on 90 rolls, 15 for that one, 15 for that one, everyone gets an equal chance, so it's 15 for all of them. So in 90 rolls, each one would be 15. So the number 3 would come up 15 times. What if we talked about how many times you could roll an even? Well, we know that the probability of getting an even is 1 out of every 2, which means every other roll, hypothetically, would be odd or even if you roll the number cube. Well, again, if 1 even out of every 2 is how many evens out of 90, when you cross multiply and solve, you'll get 1 times 90 is 90, divided by 2 is 45, which also makes sense because if you just do half of your 90 rolls is an even, that would be 45. You also could do the same example that we did over here. This one, and this one are my evens, and 15 plus 15 plus 15 is, of course, 45 evens. Let's go back to the same scenario of rolling a regular normal number cube, 6 sides, 1 through 6. What's the probability of rolling a 2? As you guys know, there are 6 possible outcomes. Out of those 6 possible outcomes, one of them is the number 2. Not 2 out of 6, there's only 1 2 out of 6. In theory, the probability of rolling a 2 is 1 out of 6. Now the question is, since theoretically there should be 1 2 rolled every 6 rolls, is that actually what's going to happen? If I rolled a number cube 6 times, would I get a 1, a 2, a 3, a 4, a 5, and a 6? And the answer is probably not. So there is a difference between theory and what actually happens. We've discussed how many 2s we expect in 12 rolls, 30 rolls. You could just multiply or cross multiply. If we actually did an experiment to determine how many 2s we got in 6 rolls, or 12 rolls, or 30 rolls, or 300 rolls, that is a difference between what's called the theoretical probability and the experimental probability, also referred to as the relative frequency. So the theoretical probability is in theory using math. So again, the theoretical probability is that formula success over the total number of things that can happen. We still do a fraction for experimental probability, but you have to do an experiment first. So if you don't do an experiment, you can't determine what the probability is. The experimental probability can sometimes be weird, because if I don't do enough trials, in other words, if I don't roll the number cube in this instance enough times, my data might look weird. I might roll the number cube 1 time, and out of that one roll, I may get a 5. Therefore, it would appear that I've gotten 0 2s out of my one roll. So in experimental probability, it would be a 0% chance of getting a 2, which is obviously not the case. We know it's a 1 out of 6 chance, or a 16.6 repeating percent chance. I also could have, when I rolled that number cube, I could have rolled it 1 time, and maybe I got the 2, which would indicate that I'm going to get a 2 100% of the time. So when you do a small number of trials, in this case just 1, your numbers are going to look weird. You really need to do a lot of trials to make sure that your experimental probability eventually looks like the theoretical probability. Because if you do the experiment long enough, it will look like the theoretical probability. That's called the law of large numbers. The law of large numbers says that you need to do more trials. And the more trials that you do, eventually it will always go to the theoretical probability. So experimental probability will always turn into theoretical if you do enough trials. Theoretical versus experimental probability of rolling a 3 has to be done by actually doing an experiment. So to compare the theoretical, which we know for rolling a 3 is 1 out of 6, and there's 6 outcomes, one of them is a 3. Let's say I rolled a number cube 5 times. And if I roll the number cube 5 times, and here's a dice roller, so I'll roll it 5 times. Ready? 1, okay, so that's 0 for 1. 2, that's 0 for 2. 3, that's 0 for 3. 4, that's 0 for 4. And 5, that's 0 for 5. So in theory, the theoretical probability of getting a 3 is 0 out of 5. Note that the denominator does not have to be 6. I only did 5 trials. What if I kept going and I did more trials? Let's keep doing more trials. So it's 0 for 5 now. Now it's 1 for 6. So awesomely enough, it turned into 1 out of 6. More trials, it's going to be better, as I said. But let's keep doing more trials. Let's do another trial. Now it's 1 out of 7, because 7 trials I did not get a 5. And you can keep going. You don't necessarily have to do the trials. You can also see how many of each result you got. That could be the experimental probability. Here's an example of experimental probability. Mike has attempted 84 free throws. So he has done an experiment. Of those attempted, 63 have gone in. Based on this rate, what's the probability the next one will go in? So in his experiment, he took 84 trials, 63 went in. 63 out of 84 reduces to 3/4, which would be choice J. This one is theoretical probability because she didn't reach into the bag. This is saying how many balloons there are. So in theory, there are 55 balloons. What's the probability that she will choose a green? Well, out of those 55 are 22, which is simplifies to 2/5. Here's one more example of a relative frequency or experimental probability question. So the bag contains balls that are either red, blue, green, or yellow. Sarah reaches into the bag, pulls out a color, and records it. So this is the result of what Sarah did. As you can see, there are 6 times red was chosen, 4 times blue was chosen, 2 times green was chosen, and 0 times yellow was chosen. The question asks the relative frequency of red. Well, first let's add this up. So how many times was a ball taken out, looked at, recorded, and put down? Looks like 12. Out of the 12, how many times was it red? 6 out of 12, which means 50% of the time it was red. Out of the 12, how many times was it blue? 4 out of the 12, which means 33.33% it was blue. And out of the 12, 0 were yellow, which means 0% of the time it was yellow. Does that mean that there are no yellows in the bag? Of course not. It just means that no yellows were chosen. If you did this a bunch more times, not just 12, eventually you will find out what the percentage of yellow is. You could then use that percentage based on how many balls are in the bag to determine how many total yellows there are. Those are things that you can work backwards and figure out using relative frequency and making predictions based on probability.